Hello everyone. Okay, so in my previous video about doing stuff in Debug in DOS, I talked a bit about interrupts, software interrupt routines, and how to access them directly in memory, how to find the interrupt vector table, or IVT, which shows you where the vectors are, or where the interrupts are in memory, and how to jump to them directly if, for whatever reason, you can't call them using an operating system, for example. In this video, I want to talk a bit about how to make bootable storage media, specifically a floppy disk. I know floppy disks are kind of old, but this is the simplest way to show it, and then later on you can get into more advanced stuff. But I want to show what happens when you boot something directly without an operating system. And the reason why I made the previous video about interrupts was because I got interested in writing a program that does run without an operating system. So most of the software that you use, of course, you run from an operating system, whether you use Windows or Linux or Mac OS or something else. But usually, you have an operating system running which provides some kind of a user interface, and then within that user interface, you start your programs, whatever program you want to run. But it is, of course, possible to make a program that runs, that boots directly from the BIOS without an operating system in between. And I think this used to be more common. In the 80s, it was not that uncommon to have games for PCs. I think they were called just booter games, like PC booter games, that didn't run under DOS, but rather boot directly from the storage medium, which was probably usually a floppy disk. It's not very common these days to make software that runs without an operating system, but it can be done, and I got interested in how to do it. So that's kind of my goal here, and that's why I made the previous video, because if you're going to do something like that, you probably can't rely on an operating system to provide you with a bunch of interrupts. So just for reference, what you're seeing here is not DOSBox again. This is actually just an installation of FreeDOS running in Box, B-O-C-H-S. Box is it's just a PC emulator, a free open source PC emulator, and I just installed FreeDOS within it. So that's what you're seeing here. So when you do a direct boot, like when you write a program that's going to boot directly from the BIOS instead of from an operating system, there are two main things that are different from writing in assembly language or machine language for DOS. The first thing is, if I just run debug here quickly and do a dump from within debug, what you'll see here, what you might notice is it's starting from 100 up there. It's starting from an address offset of 100 hexadecimal. And that's just the typical offset that's used by COM programs in DOS. If you ever make like a COM, like a .com file to run in DOS, it usually does this. Usually the code starts running with a reference offset of 100 hexadecimal. Well, if you're not booting from DOS, but you're booting directly from the BIOS, you're making like a booter program that runs directly, that boots directly from the storage media, then that offset becomes 7C00 hexadecimal. So any reference, any memory offset address that you write in your code with reference to 100 hexadecimal now has to be done with reference to 7C00 hexadecimal. It's not a huge difference. It doesn't necessarily massively impact how you write your software, but it is something you have to keep in mind. The second thing that's different, of course, is you don't have any of the interrupt routines. You don't have any software interrupt routines which would normally be provided by your operating system, such as DOS. And if you don't know which interrupts are provided by the BIOS and which ones are provided by DOS, there is this, the information can be found. This, for example, is a program called Help PC. You can still find it and download it and run it. It runs in DOSBox and in Box and emulators like that without trouble. For some reason here in Box, it did not run until I ran that build.bat file. I don't know the reason for that. I don't know why I had to run build.bat. Normally in like DOSBox, it just runs flawlessly without me even having to prepare anything. But here I had to rebuild the indexes, which is what build.bat does. I don't know why. But if you don't want to find or run this program, you can also find this information online. If you just Google it, like if I Google right now help PC, I find, for example, there's a site called stanislavs.org, which has a mirror of all the information in this program. online on the web so that you don't have to install software, you just look it up on the web. There appears to be also one on, there's also one on helppc.netcore2k.net, which even emulates the same sort of visual style of this program. But anyway, but I'll show it here. I'll show you how it looks here. So this is Help PC. It has a bunch of information on different things. Like here's information on assembler programming topics, so you can see all the different. This is mostly the different instructions, so the different assembler mnemonics and how they work. So like for example, OR. This shows you what the OR instruction does. And then for C, there's a bunch of, again, this is mostly the functions in the standard C library. So here you can see, you can get information about how to use different functions in C, like the classic printf, for example. Here's printf. Oh, and there's even a separate article on printf spec. This tells you how the format for printf works. So yeah, I mean, this program is definitely pretty cool. It was definitely very useful back in the day. Today, it might be of somewhat less usefulness, unless you are in fact doing assembly programming for DOS. Obviously, as you can see in the upper right, it's from 1991, so the information is current up to 1991. That means obviously here you won't find any information on 64-bit opcodes. Actually, I'm not even sure if will you find 32-bit? Hold on, if you go to 8086 architecture, yeah, here it talks about the 8-bit and the 16-bit registers, but it mentions the 386 registers as well. Yeah, so it does mention EX, EBX, ECX, and EDX, which are the 32-bit registers from 386 and up. Oh, and also has these special registers from, I guess, yeah, they already had 386s in 1991, so this does include information on that. So that's nice, but obviously there won't be any 64-bit information here. But anyway, what I wanted to show here was the interrupt list. So here it has a bunch of information on the different interrupts. Interrupts in different subfunctions. Here you can see there's a whole bunch of subfunctions from interrupt 21, which again is provided by MS-DOS and PC-DOS and clones of it. But what I really wanted to look at here was, here if you just go to interrupt table. So here we go. So here are the, interestingly, these are the interrupts as defined by Intel. And there we go. But these are the interrupts that are actually, okay, well, these are the IRQs. So these are, on the left you see the IRQs and what software interrupt routine they correspond to. But here you have the actual interrupt table, the actual full list of software interrupts. So you can see, for example, IRQ7 is actually supplied by int number F. So you can see how they correlate to each other. But you can also see which ones are supplied by the BIOS. So anything here that says BIOS as the location is supplied by the BIOS. And then anything here that says DOS is supplied by your operating system, meaning you're not going to have it if you don't boot DOS. So anything from int 20 to 20F or 2F, as you can see here, all of those come from DOS. And then down here there's more stuff from the BIOS, which I don't know. I have to be honest, I don't know how much of this is actually available on PCs today. I mean, I'm pretty sure that any PC today will still do stuff with interrupt 10, because that's the video, and obviously video is pretty important. But stuff like 48, int 48 is the PC Junior cordless keyboard translation. Are there really still interrupt routines in PC clones today that actually still have cordless keyboard translation routines for PC Junior keyboards? I mean, technically, if the BIOS doesn't have that, it's not really a PC compatible BIOS. Technically, you can say it's not a PC compatible if it doesn't incorporate these routines. But somehow I'm just a bit skeptical that the BIOS in PCs that you buy today would still have these routines. I don't know. But anyway, I'm not going to worry about that right now. But yeah, definitely int 10 should function. What's also probably going to be useful is something like int 16, which is obviously, as you can see, keyboard services, and probably also, maybe some of these others as well. Some of these Some of these I'm a little bit skeptical about that they would actually still exist. I'm actually curious if some of these, like for example, in 13 is disk I/O. That seems like a nice idea, but I actually don't know if this would. Does this work with IDE drives, or is this something like? Yeah, I actually don't know if these would work with a real hard drive today. Because I think if you're doing, I used to do a little bit with IDE programming, so I don't know if I don't think I used Interrupt 13, or did I? I think it's probably something different. I don't know. I don't know the details of all these interrupts and how they would still work today. But that's not really what's important. What we're looking at here is. For this video, we'll focus on interrupt 10 because that controls the video, and that's obviously pretty important. And even here, there's stuff like subfunction 4 of interrupt 10 is to read the light pen. Are there really routines for light pens? This is so old. Like, how long has it been since PCs had light pens? And I really don't think that PCs today would have that. But anyway, but one thing that should definitely work is interrupt 10.0 because that sets the video mode. That's the one that I used in the previous video, which somehow corrupted the output. And by the way, meanwhile, I found out the reason why that made the screen go all weird in my previous video. It's just because I ran the PC emulator in that video in EGA mode, but I tried to set a VGA video mode. There's a separate program called Run VGA, which I should have run if I wanted to use a VGA video mode. I didn't realize that. Anyway, so what do we want to do here? What I probably will do is just use interrupt 10 to do a simple kind of hello world programs, run a program that shows hello world or some other text like that on the screen. What a lot of people do when they start trying to do something like this, they will think, hey, let's use interrupt 10.9. Now, interrupt 10.9 is, it works. And probably what I'll do here, I'll just briefly show you how it works, just so you get an idea of how it works. But the thing is, notice there at the bottom it says it does not move the cursor. That means that every time you use this, if you want to write a string with this, you have to keep running, like for every character you have to run this, and then you would have to reset the cursor position, probably using int 10.2. So you'd have to run int 10.2 to move the cursor along one space. So you'd have to keep running int 10.9 and 10.2 and keep alternating between the two for every character. You can do that. I mean, I have seen programs that do this in a loop. They just do like a for loop, or the assembler equivalent of a for loop to run in 10.9 and 10.2. So you keep printing one character, bumping the cursor to the next space, print the character, move the cursor along. You can do that. It's very cumbersome in my opinion. I will not do that for my finished program, but just so you can see how that works, let's go ahead and briefly write a program here in Debug. I'll call it int10.9.com so we can see how that works. And I'll go ahead and start assembling from location 100 as usual. So let's start with doing a move into AH of 9. So this tells interrupt 10 that you want function number 9, which again is print a character. And then we need to move into AL. We need to say what character it is. I'll go ahead and say, I don't know, in the test program I just did a uppercase letter H because I wanted to write hello world, but I didn't want to actually write all the characters. I just wanted to write the first character. So I'll do 48. 48 hexadecimal is, I believe, the ASCII code for an uppercase letter H. We should specify in BH the page number, which I think is going to be, let's just use page 0, that's fine. And then in BL you want to put the attribute. So the way that the attribute works is basically you have a 2-digit hexadecimal number. It's a 16-bit, not 16-bit, 8-bit hexadecimal number. And the first nibble, if you will, the first 4-bit digit here, the first 4-bit hexadecimal digit, specifies the background color, and then the second one is the foreground color. So I'm going to use 0 for a background color because that's black, and then I'm going to use 7 for a foreground color because that's this normal light gray color that the DOS prompt uses by default. And then in CX we need to specify how many times we want to print the character. Let's go ahead and, I mean, normally I'd do 1, but let's do something really wild and crazy and do 10. Actually, it'll be hexadecimal 10, so that's going to be then, I guess, 16. Yeah, it'll be then 16 decimal. Okay, that's fine. Doesn't really matter. And then we'll want to say int 10. And then we want to go ahead and so that will run the program, but then because we're writing in assembler, we want to call the interrupt to end the program. So we can do that by moving into AH4C and then calling interrupt 21, which obviously again will not work in DOS, but or it will not work without DOS, but that's okay. We're running here in FreeDOS, so FreeDOS of course applies interrupt 21. So there we go. So there we've got our assembled program in memory. I just need to change CX to specify how many bytes to write. That is, hold on, how many bytes is that? That should be that is gonna be, I guess, 17. That's 17 bytes. Okay, it's 17 bytes, but I need to write the number in hexadecimal. So 17 in hexadecimal is just hold on, what is 17 in hexadecimal? It's no, I'm not quite sure of myself. I want to say 11. Is that right? Hold on, what is 17 in hexadecimal? Of course, if I Google 17 in hexadecimal, I get 17 hexadecimal is 23 decimal. That's not what I want. Okay, 17 in decimal. Yeah, it is 11 hexadecimal. Okay, so I'll write 11 here, and then I'll just say W, so it writes 11 bytes. That means 17 bytes because it's showing hexadecimal here. And let me just quickly open that up again. Did I do that right? Somehow I'm just not quite confident of myself here. Did I actually get all the... Yeah, looks like I did. Okay. Everything's there. Okay, fine. Okay, so we run int 109. There we go. It did, in fact, print H 16 times, and it, I think we only see it, yeah, we only see it here 12 times because the C:\\/ bracket is actually covering up the first instances of it, but yeah, it did, in fact, print it 16, or I guess actually 17 times, isn't it? Yeah, I think, hold on, F in hexadecimal is actually 15, so it should be, I wrote 10 hexadecimal, so it should be actually 16 times then. Yeah, okay, anyway, whatever. But that's basically how you use int 10 9. And if you wanna just briefly see how the attribute changes the colors, let's just go ahead and quickly see here. So the attribute is at address 107. So let's say enter into 107. Let's see. So what's a good background color? Let's use maybe like a red background. I believe red is 4, and then for the text color we can use maybe like let's use light blue, which is 9. So there we go. So now we've set the attribute to 4 for red background and 9 for light blue text. Go and write that again and quit, and let's do int 109. There you go. Now it looks like that. Red background, light blue text. So that's how you use that is how you use int 10 9. But I'm not going to do that for our main program. What I'm going to go ahead and do is show you how to make a program that that writes text using interrupt 10e. So let's go ahead and sorry, gosh. Let's go ahead and come back here, take a look at interrupt 10e, and so here's what you do. You set AH to E hexadecimal, AL again becomes the ASCII code for the character to write, BH is the page number, BL is the foreground pixel color as before, But what is different here is the cursor advances after the write. So it actually does bump the cursor along, so you don't have to keep using int 10.2 to move the cursor. So actually, it's pretty much the same thing now that I think about it. I didn't really notice that it uses pretty much the same functionality, but that's fine. So let's go ahead and get out of this, and I'll go ahead and start compiling this program in not in memory as usual. I guess I will. I'll start in memory. Hold on. Let me go back to debug and let me show you something first of all. So I've got a disk in the drive, or I've got a virtual floppy disk in the virtual floppy drive of this machine running in box. And let me go ahead and do this. If you use debug's L command for load, I can actually load the boot sector of the floppy disk. So I'll say load into memory space 100 and then 001. So the first 0 tells you which drive to use. 0 is drive A, the first floppy drive, and then the second 0 is the sector number. Sector 0 is the boot sector, and then the 1 specifies how many sectors I want to load. I just want to load 1 at this point. So this should have loaded it now into, yeah, there we go. This is the actual boot sector of the floppy disk that I've loaded into memory. And notice, by the way, notice the text here, this is not a bootable disk. Please insert a bootable floppy and press any key to try again. This is where that error message comes from. If you've ever in DOS put a floppy disk into the drive, if you used DOS back in the day, this has probably happened to you several times. You had a non-system disk, a non-bootable floppy disk in the floppy drive, and then you rebooted your computer, and the BIOS tried to boot from the floppy, and you got an error like, I think the usual error back then was non-system disk or disk error. That error does not come from the BIOS. That error is actually coming from the floppy. So even though the floppy claims that it's not a bootable floppy disk, in fact, it is booting from the floppy disk. The reason why you see this message, this is not a bootable disk, is in fact because from that floppy disk, it boot a program that prints, this is not a bootable disk. So it's lying a little bit. It's kind of like that painting that says this is not a pipe, even though it is obviously a pipe. It says this is not a bootable disk, but it is in fact booting from the disk to give you that error message, because the function that gives you that error message is in fact the bootable program on the disk. So that's a little bit of interesting trivia. Now you know, because if the BIOS can't boot from a disk at all, it will usually say something like no operating system or something. It just says no operating system. But the more verbose error, non-system disk or disk error, comes from the floppy disk itself. Okay, let's go ahead and start assembling a program from address 100. I'm going to go ahead and write it to the disk when I'm done. So what we start by doing is I have the program code here in front of me, so I'm just gonna read it off to you folks. You start off by doing push CS and then pop DS. The reason why you do that is what this does is this actually sets DS to be the current code segment. And that is important because, hold on, why is it important now? It's not because of int 10e. I believe it's because of, it's because of the LODS. That's right. It's because of the LODSB instruction that I'm using later. Okay, so I'll come back to that later. But for now, let's go ahead and move on, and let's say move CX. For now, I'm going to go ahead and let's see. Do I want to? I don't want to type in the whole program because I've got a whole program in front of me that I wrote earlier, but most of the program is just the string. So rather than typing in the whole string, because that's going to take a while, I'll just do 8 characters. That's fine. 8 will be enough to demonstrate how it works. So we move 8 into CX, that's the number of characters to print. And then what we want to do is into SI, we'll move the offset of the message. Now, the message is going to be at 7C15 hexadecimal. How do I know that? Because I already assembled the program, and I know that that's how big it ends up being in memory. And then at this location, right, at this location we do LODSB. So you might ask, what does LODSB do? Basically what it does is it takes the memory location from DSSI. So DS is like it's the data segment. It becomes the segment pointer. And then SI is the, what does it stand for? Not stack interrupt. Stack indicator? I don't know. But it gets whatever is located at DSSI, and it loads that into AL. And AL is what contains the character that we want to print. So after we do LODSB, then the character at that location gets loaded into AL. And I'm using 7C15 because this whole program is 15 bytes long. And remember I said before you need to do everything here with reference to an address offset of 7C00. This is what I'm talking about. In an ordinary DOS COM program, you would use 115. Here you have to use 7C15 because this program is going to boot directly from the BIOS, and the program is 15 bytes long, and then after that comes the actual string. So okay, so after you do LODSB, then I'll move into AH, I'll move E. That tells interrupt 10 that I want function interrupt 10E, which means print character and advance cursor. Then we can run interrupt 10, and then what we want to do is decrement CX and compare CX with 0 to see if it is 0. And if it is not 0, then I'll say jump if not equal. So jump if it's not 0, then jump to not 108. I was tempted to put in 108, but no, it's not 108. It's, again, see, this is the kind of thing that'll mess you up if you're writing in debug here. You look at 108 and see, okay, jump if not equal to 108. But no, remember, this is running in an offset of 7C, so we want to do jump if not equal to 7C08. There we go. And then here at the end, let's see, why is it doing this now? Oh, you know what? I think it did it as a far. It did that as a far jump, didn't it? That is gonna that's gonna mess me up later, I think. Oh, let me just quickly take a look at the code here. So push CS is fine, pop DS is fine, move CX008, that's fine, that looks good. Yeah, move SI7C15, that's fine, LDSB, that's fine, H03, B40E, interrupt 10 is okay, decrement CX, compare CX with 0, this all matches what I have here. Okay, yeah, that's where it goes off the rails. So it does a, yeah, it's doing a far jump to 7C08, which is not really what we want. Let me just go ahead and directly put this in then. So at 111, this actually should be not, let's see, what is the machine language code that I have here? So I have 75F5. How does that look here? Oh, it shows, yeah, it actually shows it here as 108. That's okay. It's a relative jump, so it actually it shows up here as being 108 because debug is using a reference address of 100, but that's fine. It'll work correctly, or it should work correctly in the program itself, because this is a near jump that we're using, so it doesn't have to be. Okay, that's fine. And then at the end, what I'll go ahead and do is I'll just directly enter here into address 113 at the end. I'll do EBFE. So what EBFE does, you can see here it's jumping to 113, but it is at address 113. So basically, EBFE is always just jump to the current instruction. That's an easy way to just make the program halt. It just gets it into an infinite loop because it literally just keeps running itself over and over. So that's fine. So that's the program code. And then at the end, I want to go ahead and type in, let's see, I set CX to 8, which means I have room for 8 bytes. So what I wanted to do then was, let's see, I guess I'll just put in, what can I do with 8 bytes? So I can say hello and then like 3 exclamation marks. Sure, why not? Let's do that. Okay, let me just quickly look up an ASCII table so I get the ASCII values for this. There you go. Okay, I've got an ASCII table in front of me. So I'm going to start entering then at address. You can see if you look at the 4th line of the program there, it moves into SI, an address of 7C15. So beginning at address 115, I want to put in the bytes, the actual hexadecimal bytes of the message that I want to print. So let's see, capital letter H is 48, lowercase e is 65, L is 6C, so I'll do 6C twice, 6C, 6C, and then hello is 6F. And then an exclamation mark is, where's exclamation mark? Exclamation mark is hexadecimal 21. So I'll do 21 3 times. And now what we have, if we do a dump, you will see, there we have it. There you can see on the right-hand side, there's hello followed by 3 exclamation marks. That is, in fact, the, that is the text that we've put in essentially. Okay, so what I need to go ahead and do now, normally I would do RCX and then W if I was writing to a file, but we're not writing to a file here. We are writing directly to that floppy disk's boot sector. So what we need to do is not use debug's, well actually I was going to say we don't use debug's W command, but we do use debug's W command, but what we use is a command like W100.001. So what this will do is this will write whatever's at memory location 100 and write it to sector 0 of the first disk drive, which is our floppy drive. So W100.001, this should write our program that we've just written directly to drive A, the floppy disk. Okay, so I'll go ahead and quit out of this. There are other ways of doing this. I mean, if you have a program that you want to write directly to the floppy disk, to the boot sector of the floppy disk to make a bootable floppy out of it. In Windows, there are several third-party programs which will do it. Like one is raw write. It's written like that, raw write, because it kind of combines the W from the 2 words into one W. So that's a Windows program that'll do it. In Linux, if you're in Linux and you have a file that you want to write to the boot sector of the floppy, you can do something like just cat the name of the, whatever the name of the file, .img for example, and then say, and then redirect the output to dev fd0, the floppy drive. Or in Linux, you can also use dd, of course, so you can say like the input file is whatever .img, and then output file is, again, dev fd0. Both of these should work under Linux. In DOS, what you can also do, I mean, I've done it using Debug. What you can do is, if you have the Norton Utilities, which I do actually have Norton Utilities 7 here, there is a program in the Norton Utilities 7 called Disk Edit, which will actually show you the, yeah, okay, it's running in read-only mode. Let's go ahead and load, yeah, physical disk floppy drive A. Let's take a look. It asks what the size is. Actually, I think it's a 1.4 meg floppy disk. Yeah, here you go. And you can actually see here, you can see, it actually shows, it gives you a nice little GUI showing you the text on the floppy, and you can even edit it here by hand. And there's even a mouse, like you can even use the mouse here if you want. So this is maybe a nicer way to do it. This is the boot sector of the floppy. You might notice this program numbers disk cylinders starting from 0 and disk sides, that means disk heads, starting from 0, but it numbers sectors starting from 1. Don't ask me why. I don't know why it does that. That's just how this program does it, and I think that might be a standard actually. I don't know. Anyway, but one thing you might also notice here in passing, most of the sector is zeros, but right here at the end, there are 2 bytes, 55 and AA. What is that all about? Well, it turns out that in order for a drive to be bootable, officially the first sector, the boot sector, needs to end with these 2 bytes, 55 and AA. Whether the disk will actually boot in practice seems to be implementation dependent. I can say I did some testing with VirtualBox, which is another PC virtualizer from Oracle Corporation, and VirtualBox seems to happily boot disks that don't have these 2 bytes in place. However, Box will not. Box, if you try to boot a disk that doesn't have these 2 bytes at the end, Box will actually complain that the disk is not bootable and give you an error, and it will not boot from that disk. I actually made this. I created this floppy image with Box's own disk creation utility, which is probably why I put these 2 bytes at the end, because this is supposed to be a bootable disk, or actually it's not supposed to be a bootable disk, but in order to show that error, in order to show this error up here, this is not a bootable disk, it has to be a bootable disk. That's kind of the irony. It has to be a bootable disk, which means they had to put 55AA at the end there. Okay, anyway, so I mean, this is kind of a nice way to do things. If you have the Norton Utilities, I think they're probably, you can find them online fairly easily these days, because, you know, they were an important set of tools for DOS back in the day, but nobody uses DOS these days. Certainly Symantec doesn't sell the Norton Utilities anymore. But anyway, that's it. So we have gone ahead and written our program here, and you can see everything there up to the hello and then 3 exclamation marks. That is our program on the boot sector of the floppy. So let's go ahead and I'm going to go ahead and click the reset button in Box to reset this computer. And I think what I'll probably need to do is press F12. I think Box, yeah, F12 for boot menu. And I can choose to boot from floppy, hard disk, or CD. So I'll press 1 for floppy. There we go, and it actually worked. So we have just made a program that actually boots directly from the BIOS. This program is completely independent of an operating system. It does not use any DOS system calls of any kind. It runs completely using just a routine supplied by the BIOS. And it shows a message on the screen, and it is pretty much just a hello world program. It doesn't do much more than that. But that's a start. I mean, that's where it all starts. So now you know how to write a program that boots directly and is completely independent of any operating system. That's all I really wanted to show with this video. So maybe in future videos I'll show how to do more fancy tricks with programs like this that run without an operating system. But I think for this, that will suffice for now. So I hope that this was interesting. I hope that this was somehow informative. I hope that you folks, if any of you are into this stuff, then I hope that you learned something. Any questions or comments? I welcome any feedback from anybody who saw this and has any opinions or thoughts to offer on it. And yeah, I guess that will be it for now. So thanks for watching, everyone. I will go ahead and call the video here. This has been making bootable programs that boot directly from BIOS in DOS from the DOS prompt using DOS debug, or in this case, FreeDOS debug. So yeah, thanks for watching everyone. I will see you in future videos. Until then, bye-bye for now.